Okay, first problem. Problem 1, recitation 3. There is a thermocouple which is formed by soldering end-to-end wires of 0.5 millimeter diameter. So it has a radius of 0.25 millimeters, or in other words, 0.00025 meters. The thermal diffusivity of the material is given, 5.3 times 10 to minus 6 meters squared per second. And the conductivity of the material is given as 19.1 watts per meter Kelvin. The probe initially at 30 degrees centigrade, so T0, is given as 30 degrees centigrade, and is placed in a fluid at 600 centigrade to measure the temperature of the fluid. So my system is basically, I have a fluid here, or maybe a liquid, and I want to measure the temperature of this using a thermocouple. Right? This is at T0, the fluid is at T infinity, and I want to see how the temperature is going to evolve. In part A, if the convective heat transfer coefficient between the wire and the fluid is, let's write it here, H is given as 85 watts per meter squared Kelvin. Determine whether you can apply the lumped heat transfer method to solve for the thermocouple temperature. So basically, we should test the lumped capacitance assumption. By checking the bio number, right? We should estimate the bio number. Anybody who remembers the bio number? What is that?
HL characteristic divided by K.
Exactly, HL characteristic divided by K. Okay. For cylindrical geometry, I mean, L characteristic is basically V over A surface. For the cylindrical geometry, I have pi r squared L over 2 pi RL, right? That's the surface area. And after the simplifications, I get R over 2 for this cylinder. And the bio number is equal to, H is given as 85. L characteristic is basically R over 2, which is 0.00025 meters per divided by 2, divided by K is given 19.1 watt per meter Kelvin. All the units cancel nicely, and the bio number comes out to be unitless, as we know. And you should get something like 5.56 times 10 to minus 4, right? I'm working with two significant figures, so let me make this two significant figures. Okay, good. And it is smaller than 0.1, which means that it's much, much less than 1. Okay. Thus, what do we say? Lumped, oops. Lumped capacitance model is valid. It holds. So I can assume it to be correct, and I can assume that the temperature is almost uniform at all times within the thermocouple. Okay. Assume uniform, almost uniform temperature profile within the thermocouple at all times. It's going to change with time, but each time, if you draw the profile, it should look pretty much uniform. Okay. In part B, it says calculate the time taken for the thermocouple to reach 598 centigrade. Okay, so basically, it asks you to find the time T for temperature to be equal to 598 degrees centigrade, or in other words, if TT is 598 centigrade, what is T? Lowercase t. Okay, how much time should elapse for the temperature to come to 598? What does it mean? It means after how much time my temperature is going to be almost equal to the fluid temperature, maybe 2 degrees less than the fluid temperature. In other words, I want to quantify how long it takes for this thing to equilibrate. Or, in other words, I want to find out what is the waiting time for this thermometer, because that's going to actually be like performance of the thermometer, right? If it actually gives me this value faster, really in a really short time, that means it's a really good thermometer which actually equilibrates fast. If it gives me this temperature with a really long time, then that might actually not be something that I need. Like for example, probably most of you are using these like medical temperatures, right, to get your body temperature, and it generally takes time for you to get the right answer or for you to get the equilibrium value. And some thermometers actually, like, you need to wait like for ages for them to equilibrate, and some give you like does a really good job to give you the correct temperature in a short time. So we're just going to basically evaluate the performance of this thermometer. So that's a practical calculation. Okay. So I'm going to use the following equation that we have done. Let me go back to our unsteady state heat transfer. I guess it was 6.1. Remember this, these class notes, right? And here, this formula we have, right? We're going to use that formula. And it's basically, you can also think of it as this part, the right-hand side within the exponential. This tau, basically, you can calculate it from here. Okay. So, in other words, it's going to be the exponential of minus this thing. Okay, so let's go back. here, we say T minus T infinity divided by T0 minus T infinity is equal to exponential minus, now, so I should have H area of the solid, surface area of the solid, divided by rho Cp V T, right? Well, I know this thing is given, this is given, this is given, this is given, right? The final temperature. This is the question. H is given. Well, AS over V, we calculated here, the other one, V over AS, but you know that it's it's going to be 2 over R, right? So it's given. How about the rho Cp? Rho Cp is not given, but you can use alpha and K to reconstruct it, because you know that the K over rho Cp is alpha, and alpha is given, K is given. So we can solve for rho Cp. Rho Cp is nothing but K over alpha. So you can actually use this one instead. Okay, so let's plug in the numbers. T is given as 598 degrees centigrade. Now I should use Kelvins, but when you think about the differences in centigrades are the same thing as the differences in Kelvins. So I have no problem with using centigrade here, because I'm going to take the difference of the temperatures. 600 centigrade divided by T0 is 30 centigrade minus 600 centigrade. That's equal to exponential minus H is 85. Let me forget about the units for the time being, just for the sake of simplicity. As long as I'm using the SI units, I should be fine. Okay. Make sure to convert all the centimeters to meters, all the hours to seconds, all the watts, like kilowatts to watts, for example. Okay, so we've worked with SI units. Times AS over V is 2 over R, so we have 2 here, we have R here, 0.00025 meters. Yeah, let me forget about the meter for the time being. And then divided by rho Cp, which is K over alpha, and K is 19.1 over alpha, but I can take it to the upside. Alpha is given as 5.3 times 10 to minus 6. Let me make sure it's SI units. Yeah, this is SI units. So good. You should make sure that everything here is SI units, except for this. This is not Kelvin, but it should be okay, because I'm going to work with the differences of the temperatures. That's it. And I have the T, I guess, right? Okay. And then if you solve this equation, you should get time is equal to something around 30 seconds. Okay. So let's comment on this. This is like significantly large, right? I mean, it takes some time. It's not giving you the temperature immediately. It takes some time, like 30 seconds is a long time. Nobody probably is not going to wait that much, especially when you're doing experiment. And if you want to like measure temperatures of many fluids within a short time interval, it might actually not be feasible for you. So this is significantly large. So you should need a better design, right? A better design is needed. So this is where chemical engineers do the task, right? To lower the value by, for instance, reducing the heat capacity. So have a look at this equation. If you reduce the heat capacity, right, to get the same answer here, you should reduce the time as well. So you should get a smaller time for a smaller heat capacity, which makes sense because it's going to take less time to heat up this thermocouple, right? You're going to need less energy to heat it up, so it's going to require less amount of time. That makes sense. You can also, and you might want to think to increase the value of H, and or increasing the value of H, meaning that you might want to swirl it a little bit while you actually take the temperature. For example, your fluid is here, right? Instead of just dunking your thermocouple, you may want to actually swirl it around so that it mixes well and the H becomes larger and the time it takes is going to get smaller, right? For instance, by swirling the liquid. Okay, there you go. So this is one problem we solved, which relates to what we have seen about unsteady state heat transfer, where we were able to do this lump capacitance assumption. Any questions so far?
What is a way that you could reduce the heat capacity?
Exactly, excellent question. So one way to change the heat capacity, not one way, I guess it's a single way, the only way, you change the material. So instead of working, for example, with material A, you work with material B. So instead of having, I don't know the heat capacities, but maybe copper and aluminum might have different heat capacities. Or maybe, yeah, I mean, you should change the material. So you should change your design. You should look for some other material. And you can also play with other things, right? You can actually reduce the R as well, right here. If you want to reduce this thing, you should reduce, sorry, if you want to increase this thing, you should reduce the R. So you can basically reduce the R, so you can actually design a thinner thermocouple for it to equilibrate faster, and which gives you a better or faster equilibration and better estimate. So this is like design type of problem. So you basically come up with the correct material and correct operating conditions to get suitable time interval for temperature estimation. So let's solve the second problem that I shared. Problem 2 of recitation 3. Says a thick concrete wall, initially at 30 centigrade, suddenly has its surface temperature increased to 600 centigrade by an intense fire which lasts for 25 minutes. 1. Write down the differential equation describing this heat transfer process. Do we need to reinvent the wheel for this problem? No, right? We're just going to use the same formula for the semi-infinite wall. So, meaning that if you take a shell, if you do your shell balance, Qx at x, Qx at x plus delta x, as you did in the unsteady state heat transfer case, you get the same differential equation, del squared T over del x squared is equal to 1 over alpha del T over del T. The problem doesn't tell you to derive it. You can just copy it from your notebook. If the problem asks you to derive it, you should show your steps. 2. If I say find or derive, then you should actually derive it. If I say write, you just need to write it. Okay. Okay. If I say write down a shell balance to derive the equation, then you should actually derive it using the shell balance and so on. The second part asks you to give the initial condition and boundary conditions. As you know, the initial condition is given as a time is equal to 0, temperature is equal to T0, which is given as 30 centigrade. That's the initial temperature of the wall. The boundary condition 1 is at x is equal to 0, T is equal to T surface, which is the temperature of the fire, right? 600 centigrade. BC2 at x goes to infinity, as x goes to infinity, T goes to T0, which is equal to 30 degrees centigrade, right? Yeah, so it's actually similar to the initial condition because the infinite end, like the other end at the infinity, does not feel anything about the fire, so it's actually not feeling any hot. It's at the original temperature 30. Part 3, what are we going to find? Let's see. We're going to find out the penetration depth, right, after a given amount of time. So it says particularly the material will disintegrate up to a depth where the temperature reaches 400 centigrade. Determine the thickness of the material which may disintegrate, meaning that what is the penetration thickness if I just take the 400 degrees centigrade, if I want to just observe the evolution of 400 degrees centigrade. Schematically, it looks like as follows. Imagine that after some time, T is equal to, T is given as, so the fire lasts for 25 minutes. Okay, good. So the initial, this is the initial temp, oops. This is the initial temperature profile, imagine. This is 600 centigrade. This is 30 degrees centigrade. And after some time, you're going to have something like this. And this is, imagine this is 400 centigrade. That means it's going to disintegrate up to this point, right? Region disintegrated. right? So I want to find out that thickness. So let's see, let's call this xd, this d for this integration. I want to find this xd. Okay. And what's given is basically, I don't need to write down the given numbers. It's all given to you and you know them. Let me write down the formula. T minus Ts divided by T0 minus Ts. This is the formula that we derived. Let me show you where we derived it. Is that 7 point? Let's see, 8.1. Yep, there you go. Okay, so it's this formula, lecture 8.1, page 3. T minus T surface divided by T0 minus T surface is equal to error function of eta. And eta is nothing but the combined variable, which is, yeah, this one, x over 2 square root of alpha t. Okay, let's go back. So that's equal to error function of x over 2 square root of alpha t. T is given, alpha is given, everything is given except for this x. Let's call it xt. We're going to find it. And let me write it here. Or maybe T is 400. Oops. 400 minus 600 TS divided by 30 minus 600. I'm using centigrades, but it doesn't matter because the differences of the centigrades are the same as the differences of Kelvin's. Error function in parentheses xt 2 times square root of alpha is given as 4.92 times 10 to minus 7 times 1500. This left-hand side gives you 0.351, and the error function of 18.4 roughly xt, and this one should be something like if you look for the error function tables, you're going to see that to get this number, you should get something roughly around 0.32. Okay. And the xt comes out to be, since 18.4 xt is 0.32, then xt comes out to be roughly 0.017 meters. Okay. And this is equal to 1.8 centimeters, or in other words, 1.7 centimeters or 17 millimeters. So 17 millimeters of the wall is going to be disintegrated within 25 minutes. Okay. And please note that I converted T from minutes to seconds. So let me write it down. Note that since we use SI units, T 25 minutes is converted to 1,500 seconds.